All right, welcome to The Explainer. Today, we're diving deep into the tech that powers tools like ChatGPT. We're going to get right into the nuts and bolts to really understand how a machine can learn to write, to reason, and even to create. Let's get right into it.
I mean, it really does feel like magic, doesn't it? But here's the thing. It's not. It's a process, a series of incredibly clever steps that all build on each other. And in this explainer, we're going to pull back the curtain on that process, starting with the most basic question of all. How does this thing actually work? Okay, so here's the game plan. We'll start with the basics, what a language model even is. Then we'll get into the transformer architecture, the thing that really changed the game. After that, we'll zoom in on self-attention, see how these models actually store facts, understand how they learn, and then we'll wrap up by looking at where this is all headed. So, let's start with the absolute basics. At its core, a large language model, or LLM, is really just a prediction engine. Its main goal in life, its obsession, is to guess the next word in a sentence. But, to do that, it has to first translate our messy human language into its native tongue, numbers.
Okay, these first two steps are just foundational. When you type in a prompt, the first thing it does is chop it up into smaller bits called tokens. But then, the real magic happens. Each one of those tokens gets turned into what's called an embedding, basically a very long list of numbers, a vector, that serves as its unique address in this huge multi-dimensional space of meaning.
And here's where it gets really cool. These coordinates, these vectors, they aren't just random. The model learns to arrange them in a very specific way so that directions in this space actually represent relationships. The math it takes to get from the vector for man to woman is the exact same math it takes to get from king to queen. It actually learns concepts like gender, or verb tense, or even capital cities as literal directions in space.
Okay, so the model gets that words are just numbers with relationships. But now what? How does it actually process them? Well, the idea of predicting text has been around for a while, but the way modern AI does it is completely different. The transformer architecture, first introduced back in 2017, was an absolute game changer. It's the engine driving this entire revolution. The big leap forward here was this total shift from thinking sequentially to thinking in parallel. See, older models, they had to read a sentence just like you and I do, one word at a time. Super slow, right? And they'd often forget what they read at the beginning of a long paragraph. Transformers, they look at the entire sentence or even the whole book all at once.
So how on earth can a model look at everything at once and not just see a total jumble of words? Well, the secret sauce is this incredibly elegant mechanism called self-attention. It's what lets every single word talk to every other word in the sentence at the exact same time, letting it figure out the context on the fly.
Put simply, self-attention is how the model figures out which words are important for understanding every other word. It's how it knows that in a sentence like, "The cat didn't chase the mouse because it was scared," the word "it" refers to the cat, not the mouse. It's all about context.
Let's break this down. It's basically like a structured conversation between all the words in a sentence. And it all kicks off with a query, which we call a query. So, each word, like creature, sends out a query vector. That's essentially asking all the other words, "Hey, anybody here relevant to me? Anyone describing me?"
Now, other words in the sentence are listening, and they're holding potential answers. This info is packed into their key vectors. You can think of these keys like little name tags or labels. The model then compares the query from creature with the keys from words like fluffy and blue.
The model then does some quick math to see how well the query from creature matches the keys from every other word. A high score means, yep, strong match. So fluffy and blue are super relevant. A low score means, nope, not related. This gives it a map of what's important for every single word.
And this is the payoff. Each word also has something called a value vector. This is its actual core meaning. The model takes the values from the words with the highest scores, fluffy and blue, and blends a piece of them into the original vector for creature. So now, the vector for creature has been updated. It's been enriched with context. It now means fluffy blue creature.
But here's the thing, it's not just one of these conversations happening, not even close. The model runs this whole query key value process many times in parallel. We call these attention heads. And each head is looking for a different kind of relationship. Maybe one head is focused on grammar, another is tracking who's doing what to whom, and a third is looking for semantic similarities. It's an incredibly rich, layered way of understanding text.
Okay, so understanding context is one thing. But these models also need to, know stuff. They need to recall facts about the world. And that's where the other big piece of the puzzle comes in, the multi-layer perceptron, or MLP. If attention is for finding context, the MLP is for knowing content.
So after the attention layers have enriched each word with all that juicy context, the updated vector gets passed to the MLP. You can think of the MLP as the model's giant distributed brain. Through all its training, it learns that when it sees certain concepts together, like the now updated vectors from Michael and Jordan, it should activate a specific neural pathway that adds the concept of basketball to the output.
And the sheer scale of this, it's honestly hard to wrap your head around. A model like GPT-3 has over 1 billion tunable knobs or parameters just in these MLP layers alone. That creates this unbelievable capacity for just soaking up and storing facts it learned from the internet.
All right, so we've got the architecture down, a stack of these blocks, each with attention for context and an MLP for content. But how does this thing actually go from being a blank slate spitting out total nonsense to writing poetry? Well, it all comes down to a multi-stage training process.
The key thing to get is that it's a two-step dance. First is pre-training. This is where the model just inhales a huge chunk of the internet with the simple goal of predicting the next word over and over and over. That teaches it grammar, facts, and even some reasoning. But then comes fine-tuning. This is like a finishing school, where it's trained on high-quality examples and gets feedback from humans to learn how to be helpful, harmless, and aligned with what we actually want.
So how does it actually learn from its mistakes? Under the hood, there's this really clever algorithm called backpropagation. Every single time the model gets a prediction wrong, this algorithm figures out how much each of its 175 billion parameters contributed to that error. Then, it just nudges every single one of those parameters a tiny, tiny bit in the right direction. Do that trillions of times, and you've got yourself a working LLM. So we've gone deep on how this incredible architecture works for language, but here's the real mind-bending part. This whole process, breaking things into tokens, using attention to find patterns, it's not just about words. And that's why the future of this technology is multimodal.
I mean, just look at this. The transformer is so incredibly flexible, it's popping up everywhere. We're now tokenizing images into little patches, videos into frames, even DNA into biological sequences. And the same fundamental principles are powering breakthroughs in everything from creating art and generating video to folding proteins and writing code. You know, we started this whole thing trying to demystify a machine, but we end up with a much, much bigger question. If we've built a single architecture that can learn the fundamental rules of human language, of visual art, and even of biology, what does that tell us? We haven't just created a clever tool for predicting the next word. We might have stumbled onto something far more profound, a kind of universal grammar for patterns that connects more of our world than we ever imagined.